Look closely at these two baked goods, a sourdough loaf and a buttermilk biscuit. Visually, they share the exact same fundamental feature: millions of microscopic pockets of gas trapped inside a solid starch matrix. Without those gas bubbles, every baked good on Earth would just be a dense, hard cracker. But how those bubbles got there couldn't be more different. One is powered by living biology, and the other is fueled by instantaneous chemistry. Today, we're breaking down the micro-engines behind leavening: yeast versus baking powder. Let's start with the biological engine, yeast. Yeast, specifically Saccharomyces cerevisiae, is a single-celled living organism. When you add it to dough, it feeds on simple sugars naturally present in the flour. As it eats, it metabolizes those sugars into carbon dioxide gas and ethanol alcohol through fermentation. Because yeast is alive, it takes time. It needs warmth, moisture, and hours of patience to continuously breathe carbon dioxide into the dough, slowly inflating an elastic gluten network. Now, enter the chemical engine, baking powder. Baking powder isn't alive, and it doesn't ferment anything. It's an instant acid-base chemical reactor packed in a single tin. It contains sodium bicarbonate, a base, an encapsulated dry acid like monocalcium phosphate, and cornstarch to keep them dry. The second water hits baking powder, the acid and base dissolve, neutralize each other, and instantly release carbon dioxide gas. No waiting, no feeding, just immediate gas production. The story of how humanity discovered these two engines spans thousands of years. For most of human history, baking relied entirely on wild yeast. Ancient Egyptians and Mesopotamians didn't know what yeast was. They just knew that if you left flour and water out, the dough mysteriously grew and tasted better. For millennia, bakers preserved starters or grabbed the foam off beer brewing barrels, known as barm. It wasn't until 1857 that Louis Pasteur finally proved that fermentation was caused by living microorganisms. For the first time in human history, we actually understood why bread rose. But what if you wanted a cake or quick bread right now without waiting hours for yeast? Before baking powder, people had to whip egg whites for an hour or mix sour milk with potash. Then came the 19th century chemical revolution. In the mid-1800s, chemists like Alfred Bird and Eben Norton Horsford developed commercial baking powders. They eventually engineered double-acting baking powder, a brilliant chemical design that releases a small burst of gas when mixed and holds the rest until it hits the heat of the oven. This single invention completely transformed home baking during the industrial era. So how do these two engines react once you put them into a hot oven? With yeast, the high heat causes a final, dramatic expansion known as oven spring. The gas bubbles expand rapidly until the temperature inside the loaf hits around 60 degrees Celsius, or 140 degrees Fahrenheit. At that precise point, the yeast dies, fermentation stops, and the surrounding starches and proteins set into a chewy, resilient crumb. With baking powder, the oven triggers the second phase of the chemical reaction. The high heat dissolves the heat-sensitive acid in double-acting powder, releasing a massive second wave of CO2. This pushes delicate batters upward before the eggs and flour solidify into a soft, tender cake texture. If both leaveners trap carbon dioxide to create an airy structure, why can't you just swap baking powder into a sourdough recipe or yeast into a pancake batter? It all comes down to flavor and texture byproducts. Because yeast ferments over hours, it generates organic acids, esters, and alcohols that create complex, savory flavors and build a strong, elastic gluten web. That gives bread its iconic chew and depth of flavor. Baking powder creates gas quickly without fermentation byproducts. It doesn't develop gluten, resulting in a tender, crumbly, cake-like texture with a neutral taste that lets ingredients like butter, sugar, and vanilla take center stage. One is a tiny biological organism working on nature's clock. The other is a precise chemical tool designed for speed and convenience. Both engineered to solve the exact same problem, making your food light, airy, and delicious. If you enjoyed this deep dive into culinary engineering, hit the like button, subscribe, and let me know in the comments which food reaction we should break down next.